Hello everyone, welcome to our presentation on BugsInDLLs. I'm Abid from the North Carolina State University, and today we'll be discussing a database of reproducible bugs in deep learning library. This work is being presented as a part of 34th ACM 6-Opt International Symposium on Software Testing and Analysis. For context, in recent years, there's been an explosion of research and tools focused on testing deep learning libraries. The literature is rich with different approaches to fuzzing. Tools like FreeFuzz, DeepRL, LatentFuzz, ASTET, etc. are designed to find elusive bugs within complex deep learning library frameworks. However, a significant challenge arises: a lack of standardized reference dataset for benchmarking these numerous testing tools. Currently, existing works often evaluate their tools by comparing bug reproduction capabilities on the same library version that they are testing on, which can introduce bias sometimes. Imagine trying to objectively compare two tools if each is only tested on a version it's already familiar with. What we need is an independent benchmark to truly understand how the state-of-the-art tools stack up against each other. However, creating such a dataset is not without its difficulties. Firstly, bugs that require GPUs to be reproduced have specific restrictions on which version of CUDA driver it can be reproduced on. Standard Python virtual environments simply cannot modify these system-level drivers. Our solution is to leverage Docker containers for GPU-related bugs. Another issue is bugs often rely on transient nightly builds. These builds can become inaccessible after a short period, sometimes just even 3 months. For example, for PyTorch, we can see that after 3 months, the nightly builds are removed from the indexes. So to solve that, we decide to build PyTorch and all the other libraries and pin the nightly versions so that we can save the wheel files. This ensures that we can reproduce it indefinitely. Herein lies the limitation of existing datasets like BugsInPy. BugsInPy is a dataset for bugs in Python, and since the deep learning libraries are written and used in Python, you can ask, why can't we use BugsInPy? But datasets like BugsInPy cannot resolve these challenges, which we aim to resolve with our tool, BugsInDLLs. So our proposed solution is BugsInDLLs, which provides 112 environments to reproduce bugs across JAX, TensorFlow, and PyTorch. It includes a command line interface for bug analysis and reproduction. It is open source and extensible. This ensures that anyone can easily contribute to the database, and it can be easily accessed, and any issues can be reported, and either the community or the authors of this paper can respond and help. As you can see here, there are a plethora of commands available in the architecture. And with list tests, we can list the tests that are available on this dataset. With run test, we can run a single test, which will reproduce a single bug in the dataset. Run tests can run all the tests. Run tool can run a benchmark with an integrated tool. Show info can show information about a specific bug with a bug ID. And stats is a utility tool that can provide different information, statistics, and different important characteristics of the bug. So as a dataset overview, we have 3 libraries, PyTorch, TensorFlow, and JAX. And from each library, we have different number of bugs. And as you can see, there are different categories depending on whether the build was a release build or a nightly build, and whether the environment was Anaconda or Docker. Anaconda is a virtual environment that we use for CPU-related bugs, and Docker is what we use for GPU-related bugs. In our dataset, we have 18 different types of bug manifestations. In this table, you will be able to see all of the categories. Among these, incorrect output is an exception. This requires a different oracle than the others. It requires an oracle which compares the outputs from CPU and GPU to ensure that there's a bug or not. For example, if we pass the same input on the same API but use separate devices, for example CPU and GPU, the expectation would be within a margin of error, the outputs should be the same. But in some cases, especially in buggy cases, the outputs have a significant difference. So for incorrect output, that is the oracle that fuzzing tools have to use. For all the other type of manifestations, we can simply either catch the exceptions or we can detect the signals raised by the code snippet. Now let's go over the selection criteria for our libraries. We selected 3 libraries: PyTorch, TensorFlow, and JAX. The reason for choosing PyTorch and TensorFlow is obvious. They are very popular, they're intensively used over multiple thousands of AI-dependent applications. JAX is a newer library, but rapidly it's gaining popularity, and people are adopting JAX into their frameworks because of its familiarity with PyTorch. So all 3 of these libraries are open source, and they have active communities, which means detecting bugs and expecting a quick response for the developers is part of the course. We select issues from specific time periods from their bug tracker. We ensure that we work with the latest bugs on the libraries so that we have an idea of the active bug scene for a specific library. And the different time periods are demonstrated here. So our bug selection process was pretty rigorous. We had a 3-stage process. In stage 1, we applied initial filters, the specific time periods that were mentioned before, the label to be bug, the status as being closed, and there being a linked pull request with the issue. Linked pull request is a demonstration of acknowledgement from the developers. It means the developers are either working on fixing the bug or they have already fixed the bug and it's already in the release build, or it's waiting to be on the release build. In this process, we get 725 PyTorch issues, TensorFlow issues at 217, and 111 JAX issues. You may notice that PyTorch has more issues than TensorFlow and JAX. The reason for this is PyTorch sometimes do not have a specific bug label. And that's why we have to do some manual inspection to ensure whether it's a true bug or not. So that's why initially we end up with a large list of issues. On stage 2, we perform the manual inspection. On this manual inspection, we check any code dependencies that we have. We assess whether the code is reproducible properly. We assess if the code has a clear description, if the bug is properly understandable, and if it is truly a bug. We also discard different non-core functionalities. For example, we discard any bugs related to documentation, and we discard any issues that are basically feature requests posed as bugs. After going through this stage, we end up with 143 PyTorch bugs, 102 TensorFlow bugs, and 80 JAX issues. And stage 3 requires a deeper analysis. We go through each bug and make sure they truly are bugs, and we didn't include any bug that would not fall into the criteria. We discard different build and installation related issues which can look like a bug. And we also discuss some API misuses, which is not an implementation bug, but it's a lack of knowledge on the usage of the API by the user. After going through this deep analysis, we finalize the list of bugs reports. And within the time period that we mentioned before, we ended up with 37 issues for PyTorch, TensorFlow had 29 issues, and 46 issues for JAX. Now let's go over the steps to add a bug to the dataset. Initially, we have to select an issue as we described before. We follow those criteria. Then we create a PyTest so that the code that is provided with that issue is written as a test that can pass if the bug is successfully triggered, and it fails if the bug is not triggered as we expect it to. After that, we identify the library version, for example, the PyTorch version, TensorFlow version, or the JAX version, and any of its additional dependencies it requires for the bug to be properly reproduced. With all these dependencies, we go to the next step and we write a requirements.txt file. But how this file is used differs depending on the architecture on the next stage. So if the bug is reproducible with CPU, we simply configure a conda environment with these requirements. But if the bug requires a CUDA driver, we write a Docker file with the respective version of the CUDA driver, and it ensures that proper drivers are loaded and installed with the Docker. After that, with this information, we have to write a script to automate the process. The task of this script is to set up the environment and run the PyTest, and it will display the result of the test. After that, we create a directory under the library with the bug ID and keep all the artifact files there. For example, the Docker file, the script, the requirements.txt, etc. Now let's go over what test oracles we use. As mentioned before, we use PyTest to test the bugs. But what might be counterintuitive is the tests actually pass if the bug is reproduced, as opposed to failing a test in real life application, where the sole purpose of a test is to fail if there's a bug. In our case, we have three different types of oracles. For the first one is the most obvious one, which is an unexpected exception. For these cases, we execute the buggy code snippet, we report the details of it, and if the exception was as the bug report mentioned or suggested, then we consider the bug to be reproduced. And otherwise, we consider that it was not reproduced and the PyTest test fails. The second one is the oracle that we talked about before, the differential oracle. But for bug reproduction, we don't have to check CPU and GPU outputs, since we already know what buggy output was found by the original user. So we just take the incorrect value that was reported with the bug, and we check if that truly was reproduced with the bug snippet. And if the PyTest passes when the incorrect value is matching with the incorrect value that we got. And the third one is a crash or a signal raised. So we expect a certain signal to be raised by these bug snippets, but that also means that the original process will crash. So instead of running it on the same process, we create a separate script that is run from a PyTest. And when the script abruptly crashes, it raises a signal, and PyTest checks whether the signal is expected or not. This is an example test oracle. As you can see, this is testing an API called fake quantize per channel affine, and it is passing all the parameters here. And the bug under test here is expected to raise a runtime error. So with pytest.raises runtime error as the info, this line ensures that the proper exception is returned, and this test will pass when this is indeed the case. And at the end, we also report and print what exception it faced, so that we can also visually see that the bug was indeed reproduced. Let's go through a usage example. For example, we will take PyTorch bug ID 120903. So on the right, you can see the description of the bug. It provides the code. It provides what output it's expecting. And at the bottom, it has information about the environment. And from this, we can see that it requires CUDA 12.1 for reproduction. It requires a PyTorch version of 2.20. It throws a runtime error with an unexpected error message, and the code snippet and environment information is provided in the bug details. And reproducing this bug with our dataset is simple. We simply have to run the command run test. And as the library name, we pass PyTorch. As the bug ID, we pass the bug ID of this bug, in this case, which is 120903. And at the right, we see different snippets of the output. So initially, it will try to recreate the environment for the bug, and it will display information about the environment. And then it will display the information of the PyTest execution. And if it passes, it will say 1 passed, meaning the bug was successfully reproduced. Another user's example shown here is for an utility function called stats. The purpose of this function is to provide different statistics about our dataset. For example, if we run stats with the library name PyTorch, it will give us different statistics about bugs that are from the PyTorch library in our dataset. So from this screenshot, we can see there are 37 PyTorch bugs. 16 of them require a GPU, 21 do not require a GPU, 19 are nightly bugs, 18 are release bugs. We can also see what the bug manifestation types are. And after that, there's a detailed breakdown on which version has which bug ID, meaning which bug can be reproduced with which version of the library. At the end, we have a try that demonstrates where the bug fixes were, so that you can get an idea of which area of the library is frequently found to be buggy. Another usage for this tool is the ability to integrate existing fuzzing tools so that we can do the evaluation, a proper evaluation using an independent benchmark. So this requires 3 different scripts from the developer of the fuzzing tool. First, we need a tool execution script. This will execute the tool in a Docker environment. So a Docker environment to build the tool is also required. A pre-processing script that will pre-process for different error types and different buggy APIs, and a post-processing script that will match the logs that we get from the expected errors we have for the bugs in that specific version. And so the process is initially you have to create a Docker container using a script to get the Docker container for a specific tool. We have to select the library version, and the library version can have anywhere from 1 to many different bug IDs. So it will try to match all of the bug IDs available for that library version with the logs it gets from the output of the tool. To run the command, it's very simple. We have to execute run tool. We pass the tool, we pass the library, we pass the version, and we pass the script that executes the tool. As a reference, in our repository, we provide an implementation for FreeFuzz, which is a very commonly used and a popular state-of-the-art. To reproduce a bug in FreeFuzz and complete an evaluation for that specific version, we can run the following command. We can run tool with FreeFuzz, PyTorch, the version, and the script provided for FreeFuzz. So the steps that are executed when we run the scripts are it reproduces the sample bug from the specified version so that it can get the environment ready. It runs the pre-processing script to get the APIs that are actually included in the bugs that are in this version so that we don't have to run all the APIs. It updates the Docker environment and with the environment of the bug. It runs FreeFuzz and it runs the post-processing script to match the log that we get from running FreeFuzz with the log we got from reproducing the bugs. And in conclusion, deep learning library testing currently lack standardized evaluation due to the absence of reproducible bug dataset and an independent benchmark. And BugsInDLLs has been implemented with the aim of resolving that. BugsInDLLs currently have 112 reproducible bugs, and it's open source, so it's easily extensible. And the community and even the authors can extend this number further to make the dataset even more robust and more effective as a benchmark. This is more than just a dataset. It offers a robust infrastructure to evaluate various fuzzers and testing techniques for deep learning libraries. Looking ahead, our future work includes continuously expanding the dataset with new bugs and exploring automated methods to front-port different bugs, essentially adapting them to different versions of a single library. We encourage you to check out BugsInDLLs and contribute to this growing resource for deep learning library testing. The QR code shown in the screen contains a link to the tool's GitHub repo and a link to the YouTube video demonstrating the usage of this tool. We hope this tool will help researchers with proper evaluation, and the community will enrich the dataset with more bugs. Thank you for your time.